thank you. So welcome everybody. It's like to the RoboSub Computer Science Team Senior Design presentation. The students have worked hard this year. It's like, and I think they've got as like an awesome project. So first off, however, it's like I would really like to thank the Office of Naval Research. It's like for creating and managing the RoboSub competition that that we've been a part of. It's like without them, none of this would have been possible. And so, you know, it's like, especially as it's an ongoing multi-year project, it's been like very, very interesting and challenging. It's like to continue on. As far as the other advisors, I would like to thank Dr. Tufenkjian and Mark Sargent, who couldn't make it here today. So without further ado, I would like to turn the presentation over to the senior design team.
Let's go ahead and get started. So my name is Carlos Gomez, and I'm here with the rest of my team, composed of Viraj, Ethan, Andres, and Daniel. And on behalf of our faculty advisors, Mark Sargent and Richard Cross, as well as our liaisons, Mark Tufenkjian and Tufenkjian, I would like to present our senior design project, RoboSub. So many of you might be wondering, what is RoboSub? Well, RoboSub, as you can see, is an international competition that challenges universities across the world to create an autonomous underwater vehicle, or AUV for short, that can complete specified tasks underwater. For Cal State LA, this project has been divided into 3 different teams: the mechanical engineering team, electrical engineering team, and computer science team. This year, we received a plethora of tasks and have narrowed it down to a couple things together as an international community. These tasks include choosing a role for the competition, using underwater object detection to identify objects, using a mechanical arm to move or grab objects, firing torpedoes at a target, or bumping into a buoy. This year our roles consist of a bootlegger or a G-man. To meet these challenges, the computer science team has divided themselves into 2 separate groups, the computer vision team and the mission planning team. Computer vision will be responsible for the camera feed on the AUV and process these images into a way that the submarine can use to position itself for the obstacles. Mission planning will take that data and help support the hardware and allow the submarine to autonomously navigate the competition course and complete the obstacles. Computer vision uses YOLO, DarkNet, and OpenCV as their challenges, while mission planning uses ROS and SMACH. The labor distribution for RoboSub is laid out here. All the hardware is handled by our EE and ME teams, which send data to us, and we will be using that to complete different things in our mission planning and CV. In no particular order, here's a task flow diagram for this year's competition. We will start by going through the gate and selecting our team, and then continue on to the buoy task, dropper, torpedo, and octagon task.
Hello, my name is Viraj, and I'll be taking over for the mission planning portion of this presentation. So I'm going to go over some technologies that we used for this project. The first one would be ROS, which is a robot operating system, which is more like a framework for robots. It has many libraries for robot programming, and it makes it easy to learn and build software projects for robots. ROS is useful for us because, firstly, the publisher-subscriber system allows messages to be sent and received anywhere in the system. This allowed us to receive data from the sensors quickly and reliably. Secondly, ROS has a very strict project workspace layout, which helped us keep our program files organized. Workspaces are made up of packages which allow us to cleanly modularize our code. And lastly, ROS, of course, is built for working on robots. As I said before, there are many built-in libraries for robot geometry to localization. And ROS is an open source project, so there are many resources available, and there's a large community of users. Next, I'm going to go over SMASH, which is short for state machine. SMASH is useful for a project, or SMASH is useful for us because it runs on ROS. It's a state machine framework, and it's straightforward Python syntax, makes it very easy to learn and very easy to implement. SMASH is useful for us because our project is made for planning high-level tasks. Mission planning is responsible for programming the behavior of the robot, which is high level. Next, we also implemented SMASH using the state machine pattern, which allows us to design, maintain, and debug complex state machines and link them together as a hierarchical state machine. And lastly, the RoboSub competition is designed similar to a state machine, so we can break down every task into its own state machine, and the state machines can be linked together seamlessly to flow from one task to another. Now I'm going to go over some mission planning challenges that we had throughout the year. Testing for our software on the submarine is very difficult because of the logistics behind testing a submarine. We must find a swimming pool approved by the RoboSub team, and all the senior design members from the electrical department and the mechanical department must be present. The code for the submarine should be prepared beforehand, and what we are testing should also be decided. The changes to the code during testing are also very, very minimal, and there's a limited amount of time we can test for. Secondly, the hardware development. Since the submarine is also being set up by the electrical and mechanical engineering teams, we usually have to wait for them to get the hardware working. The sensors are under development, so we do not know what the exact metrics and format of the data will be, and how precise the information is. Therefore, we have used mock data to develop the software, which will be replaced with real live data once the submarine is fully functioning. And lastly, of course, the shelter in place. Due to the shelter in place orders, hardware development has been stalled, which is why we're continuing with mock data and mock publishers to program our submarine. And now we have here an example state machine to show you how we planned our tasks. This state machine is for the gate task. This gate task involves finding the gate and passing through the gate. Once we pass through the gate, we can move on to the next task. Otherwise, we would have to surface if there's any errors. So I just wanted to show this task, this design to you, because all of our tasks follow the same pattern. First, we try to find the object. In this case, try to find the gate. Once we do find something, we determine whether that object is the object that we're looking for. Once it is confirmed, we move on to do the tasks associated with that object. And once we have completed that, we move on to the next task. And to the right, you can see the terminal output, which shows the successful completion of this task.
Hello, I'm Ethan Cha, and I'll be talking about OpenCV and how it was used for our project. OpenCV is an open source library of functions that are used for applications that require real-time computer vision. We plan to use OpenCV for image preprocessing, which allows the image to be clearer for us and clearer for the neural network to understand. So one of the functions that OpenCV provides to us is called thresholding. And what thresholding does is it manipulates the dark and bright regions of an image. It basically simplifies the visual data that is shown from an image. And how it works is you choose a number from 0 to 255, 255 being the brightest. And the lower you bring the threshold, the darker the image becomes. And by manipulating this value, we are allowed to grayscale the image, which could help us with visibility or readability of an image. So the next function that it provides us with is called color filtering. What this does is it chooses the colors that we don't want to image and excludes it from the image. And if we specify what colors we want in an image, it will then highlight them, as you can see in this picture, and it gives us a clearer image of what we want to see. So the second function we would be provided with is called image blurring. And the image blurring, basically, as you can see on the right, there's a lot of black spots on the image. That's considered noise. And what it does is it gets rid of the noise and leaves us with a bigger picture. Another function it provides us with is MOG Background Reduction. And this is really useful when we're using live feeds of data. And so what it does is it compares the first image that it gets from a live feed, and then the following images, it then stacks them and sees which one is different, and it highlights all the moving parts of the images and highlights them, as you can see on this image. Lastly, we researched which types of filters that are useful for our situations underwater. As you can see on the right, all three situations of shallow water, deep water with natural illumination, or deep water artificial illumination, ACE works best. But if we were only supposed to look at shallow water and deep water with natural illumination, the SP filter would be best. And if we want to see in deep water, both in natural illumination and artificial illumination, the CLAHE filter would be best.
Hello, my name is Andres Lopez-Ruiz, and I'm going to be talking very briefly about how our predictive model works. In order to be able to detect the images that were required by the competition, we had to implement a neural network. In our case, we decided to go with a framework called DarkNet. But what is a neural network? A neural network are models that use very large amounts of data to make predictions based on the features from the data that it learns from. They're mostly composed of 3 layers: an input layer, a hidden layer, and an output layer, each with its corresponding nodes that are like, the features that it learns from, and also the output labels or like data that it gives. And sometimes it uses activation functions like ReLU, which are used to give more meaningful output. But these models are just basically sets of matrices that have information to try to minimize the cost or reduce the difference between the predicted value and the actual value of the data that we have. In our case, though, we are using classification, which is a type of, we use supervised learning to predict or classify the data that we have. But these predictive models take numbers as inputs, and so how do the computer know like that these data is images? Well, to a computer, an image is just a grid of numbers that represent how dark each pixel is. We use pre-processing tools like Ethan just talked about to make it more easy for the computer to understand and to work with. But in order for us to fit an image into the neural network, we treat those images as an array of the values from the pixels that we get. However, the neural networks do not know that an image is the same regardless of its position on the image itself or the rotation that it has. So for that, we use convolutional neural networks, which it takes the principle that basically it's the same regardless of the position that it's on. And to do this, we pass a sliding window over an entire image and save each result as separate small picture tiles. Then we basically feed each image tile onto a small neural network and basically treating every tile equally, but we're gonna mark the interesting files separately. And we're gonna then save the results from each tile into a new array that only keeps the sections from the original image that we thought were interesting. Then we are gonna be using tools like downsampling like the algorithm max pooling, which will reduce the size of the arrays in order to keep just the most important bits that we obtained previously. And then we're going to make our predictions based using a fully connected neural network based on the small neural networks that we used to train. And then we're going to repeat this process back and forth using back and forth propagation.
Hello, I am Daniel Gomez, and I will be talking about how we utilized YOLO and the results we got from it. YOLO stands for You Only Look Once, and it is an object detection system. We chose YOLO because of its performance on our hardware. We are using the NVIDIA Jetson to detect, to run YOLO on the sub. We use YOLO to detect objects, to direct the sub for movement whenever we need to move towards an object. We also use it to identify objects that require further interaction, such as when we need to pick something up and put it into a bucket for a dropper task, or we need to find identify an object as a target for the torpedo task. Here's a brief overview of how YOLO would process an image. It first cuts the image into a 13 by 13 grid of cells. Each cell is responsible for 5 bounding boxes. These bounding boxes are given a confidence score. This is basically YOLO telling you how confident it is that whatever it's trying to detect is actually an object. It also gives class predictions. So this is YOLO telling you the probability that it is something that you're actually trying to predict, in this case, a dog or a bike or a car. In the end, you'll have over 800 bounding boxes and class predictions with low confidence scores. So in order to achieve the final prediction, all these confidence scores and bounding boxes are filtered to only the highest, the ones with the highest confidence scores in order to do the final prediction. This is an example of some of the results we got from our model. We were able to successfully train and detect all the images that were provided for us in the competition that we will need to be able to detect while we're in the water. Here we have an example of us detecting the bootlegger image and the money symbol image underwater. Here's a chart showing our results from our training. We were able to achieve an average loss of 0.1474 over the course of 3,600 iterations worth of training. And this concludes our presentation. And now it's time for Q&A.
So does anybody out there have any comments or questions, information they would like to get further details on? As always with a Zoom meeting, I'm going to take is a complete lack of, oh, is like Jarvis is asking, is there something actually working we can see? Gentlemen?
So as of right now, we are not able to test on the actual submarine, but before I showed a slide showing the terminal output, and for now that's the machine planning has been creating state machines based off MOG sensor data, and that's what we run the programming with. That's for the machine planning section.
For the computer vision portion, we were actually like posted on the slides. We were able to make predictions and like detect different images from the competition successfully with a pretty high success rate.
Daniel, would you have any additional results on the image recognition? You're showing the the bootlegger and money symbol. How long did that take to generate?
We let the model run overnight, so I think at least 12 hours worth of training.
Yeah, but then it was able to detect it real time after that?
We haven't been able to test for real time, but we went over the course of all of our data, and we were able to detect various images in different orientations and in different lighting.
Okay. Any other questions?
What's the frame rate of image processing? So it's a follow-up question of what was asked before. So what's the frame rate of a detection?
We haven't been able to physically run the model on the sub yet because we don't have access physically to the hardware, and we would need to put it on the sub, put it in the water to get some accurate readings. So unfortunately, we can't reliably give that sort of data.
But you know the process time, right? You know how much time it takes to process one image.
Oh, one image. Andres would have the answer. He actually ran the model. He has the computer to run the model on his system.
So, I mean, we trained the model with over 2,500 pictures for each image that we had, and we had a confidence level of like 95, 97% on the predictions that we made.
When you ran a test, though, how long did it take to recognize an image?
Well, it was actually not that long that it took in reality. Probably, I don't have the exact number, but it was like just a matter of seconds to actually, from the moment that you fed the image to the algorithm it gave you the result. But yeah, it wasn't very long at all. So, like I said, it was also with pretty good confidence levels that we had.
So possibly a follow-up research would be is they run that actually on the NVIDIA hardware and see how fast it and actually measure some data.
Right. Yeah. That'll probably be one of the things that we'll have to see. Well, and also to see how it does when we actually have the hardware connected and fed the live images directly into the algorithm too.
And also, it's very interesting. This is the first time that I've ever heard from your team say like ROS is easy. To me, I don't feel it's easy. And over the past several years, and we have been working with ROS, and so if normally during the final presentation, suddenly students say like ROS is easy to use. Is that your real feeling about using ROS?
Our team had, I feel like we had an early start with ROS, so we didn't have it as tough as teams beforehand because we were warned about that early in the year. So first off, we all started with ROS, doing tutorials and learning it. So now I believe we have a good grasp on the basics, so that allows us to build our foundation at this project.
Too bad nobody had a fish tank. You could have tried using that for your water filter and for the running the image on a simulated underwater environment.
I'd also like to add one thing that I believe was overlooked is that this competition isn't until August, and this RoboSub team will be continuing to work and develop the submarine from here until that point, should the competition still take place. As of right now, we haven't heard otherwise. So we're planning on continuing working throughout the summer to ensure that the submarine does well in that competition.
Okay. Any more questions? Comments? Observations? Okay, well, I would like to thank everybody for showing up today. It's like, this is actually an impressive crowd for the senior design presentations in our online environment here. And once again, a special shout out to the Office of Naval Research for everything that they've made possible for this this competition. And with that, I think we're done. It's like, I don't want to just close the meeting and kick everybody out, so we're just going to hang out for a little bit and chat. If anybody's got any plans for the future, we'd love to hear them.
I think I'd like to personally thank Yolanda Tanner. Thank you for taking time out of your day to come to our presentation. And thank you for your feedback in chat. It's always good to hear that Cal State LA continues to impress.
Okay. Well,
Good
hope
job.
everybody enjoys the rest of the presentation. Yes.
Mr. T. Fox has a question.
Yeah, I just wanted to make a statement. Excellent job on your presentation and for all the work that you've been doing. As you get close to the end of the finalization of your career as a senior, I do not want you to underestimate the quality of the skills that you have learned. I want you to always remember that it's not about your major, but it's about the skills that you learn within that major. And being able to know that you're going to be able to go out there and do the job that needs to get done. A problem is a solution undiscovered. So now as you get ready to graduate, and although you may not be able to walk across the stage, know that Cal State LA has prepared you for these opportunities. The opportunity that you've been afforded by working on the RoboSub team has really helped you to be able to be prepared to work for the Department of Defense. So I encourage you, if you have already done so, reach out to Dr. Tufenkjian and send him your resume so that you can apply for one of the opportunities that's available at one of the Department of Defense Office of Naval Research national laboratories and programs, because you are really prepared to go out there and make a great difference. And I'm really proud of you, and congratulations. Thank you, everybody.
Thank you.
Thank you.
Thank you, Chief Fox.
Thank you.
Okay.